If you want to get a chuckle in your physics class, ask the question, do clocks run faster during the day or at night? By the end of this video, you may change your opinion as to whether you think the question was a joke or serious. In 1971, 4 atomic clocks were flown around the world on Boeing 737 aircraft in eastward and westward directions. The purpose was to determine if time dilation actually occurs. Since the airborne clocks are moving in the same direction as Earth's 1,000 mile per hour rotation, they are traveling at 1,000 miles per hour plus the 500 miles per hour velocity of the jet. It was predicted that they would lose 40 nanoseconds during the eastward flight. Since the westbound clocks are moving opposite the direction of Earth's rotation, they are traveling at 1,000 miles per hour minus the 500 miles per hour velocity of the jet. It was predicted that they would gain 275 nanoseconds during the westward flight. At this point, you may be wondering about the original question. It doesn't seem like there would be any difference in the speeds between clocks running during the day or at night. Let's look at this from the viewpoint of an astronaut that is at a fixed point from the Sun. The Earth orbits the Sun at a velocity of about 67,000 miles per hour. Relative to the astronaut, the night clock has a velocity of 67,000 miles per hour plus 1,000 miles per hour rotational velocity plus the 500 miles per hour velocity of the jet, for a total of 68,500 miles per hour. The astronaut will see the day clock traveling at 67,000 miles per hour minus the rotational velocity minus the velocity of the plane, for a total of 65,500 miles per hour. The difference in velocity of the day and night airborne clocks is 3,000 miles per hour. That is 6 times greater than the velocity difference between the airborne clocks and the Earth clocks in the 1971 experiment. 2 observers that are at rest with respect to Earth's inertial reference frame are watching 4 airplanes fly overhead, all at the same speed but 2 in opposite directions. Relative to the observers, all airplanes are moving at the exact same speed relative to them. Regardless of direction, all 4 of the airborne clocks are required to run at precisely the same rate, but slower than the clocks on Earth. Suppose we were to repeat the clock experiment that was done in 1971. This time we're going to observe the experiment from 3 unique inertial reference frames. The first, 2 observers at rest with respect to Earth's inertial reference frame. The second, an astronaut orbiting the Sun but stationary with respect to the North Pole. And the third, an astronaut that is at a fixed point from the Sun. According to the special theory of relativity, observer 1 would require all airborne clocks to run slow and at the same rate. Observer 2 would require the eastbound clock to run slow day and night, and the westbound clock to run fast, also day and night. Observer 3 would require airborne clocks to alternately run fast then slow, depending on whether it was day or night. Whatever the results of the experiment yielded, there are going to be 2 observers in this case that will see a failed result.